The compressor casing contains the process gas and rigidly supports all stationary internal parts and the bearings. Compressor casings can be either horizontally or vertically split. Recall that vertically split casings are also referred to as barrel type. Let's start by examining a typical multi-stage horizontally split centrifugal compressor. A 3D model of this type of compressor is shown here. You can see the casing upper half and here the casing lower half. Here you can see the bearings, we'll cover them in details in a later video, the suction nozzle of the compressor, and the discharge. Let's now remove the casing upper half and view the internals. On removing the casing upper half, you can see that a diffuser assembly exists below the casing. Let's go further and remove the diffuser upper section. Now the shaft and the impellers are seen. In our example here, it becomes clear that we have 5 compression stages, since we have 5 impellers, making this compressor a 5-stage horizontally split centrifugal compressor. The shaft with the different impellers mounted onto it is called the rotor. So let's remove this rotor and examine what's below it. Now you can see the diffuser lower section. And here, the diffuser lower section with the casing lower half are seen from a different angle. Let's now observe a multi-stage vertically split centrifugal compressor or a barrel compressor. A typical cut section is depicted here. So here you have the suction nozzle of the compressor and here the discharge nozzle. The shaft, the impellers, the ballast drum, the journal bearings, and the thrust bearing, all of these internal parts that we will cover in later videos, all of them are rigidly supported by the casing. In general, barrel-type casings are used above 600 psi pressure, or for mixed gases with a high hydrogen content. From a maintenance standpoint, however, horizontally split casings are preferred. This is because these type of compressors allow easy removal of the rotor. Now, the major problem connected with casing design is distortion of the casing, caused by excessive piping or foundation forces. During construction or whenever piping is removed from the casing, dial indicators, mounted external to the casing as depicted here, should be positioned on the shaft in the horizontal and vertical planes. Movement of more than 0.002 inch when piping is bolted up to the casing should require correction to the piping system. The only way for the compressor shaft to move is if the piping or foundation cause excessive casing strain. A check for excessive casing strain caused by the foundation is commonly known as soft foot. To check for soft foot, a dial indicator is mounted external to each casing support. If the support moves more than 0.002 inch, when the support foot is unbolted, soft foot exists. Soft foot should be checked with process piping disconnected. The cause of soft foot is that the plane of the support is not parallel to the plane of the foundation, and a gap exists between the foundation and support foot, as depicted here, a soft foot for the compressor motor. The function of inlet guide vanes is to direct and distribute the gas to each impeller. Centrifugal compressor guide vanes are usually fixed. plant and instrument air compressors can be supplied with adjustable guide vanes. Axial compressors, however, are frequently supplied with adjustable guide vanes. Recall, we have seen this in a previous video, but here for reminder, an example of an axial compressor adjustable guide vanes. Here, the support ring can be rotated to change the angle of inclination of the vanes, as depicted here. Now, adjustable guide vanes alter the dynamic compressor performance curve by changing the velocity and direction of the gas relative to the impeller blades. Impact of the gas velocity vector with the blades, so counter-rotation, will increase the gas tangential velocity and therefore produce greater head. Leading the gas velocity vector, so pre-rotation of the guide vanes, will decrease the gas tangential velocity and produce less head. To help you better understand this concept, let's first examine the counter-rotation case using our impeller schematic with the two vectors acting on the gas as it exits the impeller. In case of counter-rotation of the inlet guide vanes, the velocity relative to the blades will be reduced, as depicted here. This results in a new exit gas velocity. This new exit gas velocity will have a higher x component or tangential velocity. So, a counter-rotation of the inlet guide vanes reduces the relative gas velocity, which increases the tangential velocity. This means, assuming a constant tip speed, the head is increased. Now, in the case of a pre-rotation of the inlet guide vanes, the velocity relative to the blades will be increased, as depicted here. This results in a new exit gas velocity. This new velocity will have a lower x component or tangential velocity. So, a pre-rotation of the inlet guide vanes increases the relative gas velocity, which decreases the tangential velocity. This means, assuming a constant tip speed, the head is reduced. Now, guide vanes, stationary or adjustable, positioned at an incorrect angle, can alter compressor stage head and efficiency. This problem will be discovered with stationary guide vanes during an initial shop performance test, if it is of course required by the end user, and when it is discovered, it must be corrected. However, adjustable guide vanes can be improperly set if the individual guide vanes, bushings or linkages are replaced. So my advice to you, make sure to consult the instruction book and consult the equipment vendor if necessary when replacing any components in an adjustable guide vane assembly. The rotor consists of the shaft, impellers, thrust disc, and ballast drum. The rotor rotates and therefore increases the energy of the gas. Dynamic compressor rotors can contain axial and or centrifugal impellers. Centrifugal impellers can handle flows from 100 to over 100,000 cubic feet per minute. Axial impellers are usually used above 100,000 cubic feet per minute. The head produced by a centrifugal stage can vary from 5,000 to 25,000 feet. An axial stage usually produces around 3,000 feet of head. The most common problems associated with rotors are component unbalance, rotor unbalance caused by improper impeller assembly, excessive blade or impeller stress, and rotor system natural frequencies. These topics will be of course discussed in detail later in this course. You can see here a typical multi-stage vertically split centrifugal compressor with its corresponding cut section. Let's have a closer look at one of the compressor stages. As seen in a previous video, a compressor stage is symmetrical, so we can focus only on the upper half of it. The diaphragm is the non-moving part between two stages and contains the diffuser, the return channel, and the stage seals. The diffuser converts velocity into pressure. The return channel guides the gas into the next stage. Diaphragm can be manufactured of either cast iron or cast steel. Both materials are acceptable. However, in the event of severe axial rubs caused by excessive surge, cast iron diaphragms can crack and will require replacement. Since centrifugal diaphragms are rarely spared, failure will cause long periods of downtime and loss of product revenue. Diffusers are usually vaneless, but can be vaned or scrolled to increase head produced per stage. Older designs with vaned or scrolled diffusers often encountered problems with impeller sidewall breakage, caused by fatigue of the impeller side plates resulting from alternating pressures at the impeller discharge. This phenomena was caused by the pressure buildup from blade passing interference between the impeller and diffuser vanes. The classic fix is to scroll the impeller wheel between each vane. Modern vaned diffuser designs, like the low solidity diffuser LSD, move the vane up the diffuser out of the immediate effect of the impeller vanes, as depicted here, therefore eliminating significant pressure fluctuation.